Hello again. In the notes, we are now working on the concept of modified Arrhenius theory, which is number 2. So our previous podcast was all about Arrhenius, and honestly, this is still based upon Arrhenius's theory of acids and bases. But what you should have noticed after doing the lab investigation, and honestly, if you haven't done number 1 of the assignment yet, go back and do that before you listen to this podcast. Now, you should have seen that some of the solutions really did not match Arrhenius' theory. They couldn't be well explained. So, if you can't explain everything with a theory, that means the theory needs to evolve. It has to be altered in order to match all of the evidence. There's a habit up to this point where, and honestly, it happens still quite often, but where chemists will take water and they'll completely leave it out of a reaction. Now, this should look familiar. Look at that. There's like we talked about in the previous lesson. Hydrogen chloride gas reacts when you add water to produce hydrogen H plus ions and chloride Cl negative ions, leaving out the water. Now that's all good and well, except like we said, we end up with some circumstances that can't be explained if water is left out. Now, water is an incredibly important and unique molecule, and because it has such special characteristics, honestly, we can't leave it out. It's a big deal. In this particular situation, let's consider one of the things that Arrhenius left out with the original theory. It doesn't account at all for the super strong attraction between that H plus ion that's in the solution, like hydrogen chloride gas that's been dissolved in water, with a neighboring water molecule. Now, if you think back to our very, very first unit, water is a very, very polar molecule. In fact, it is so polar that it participates in its very own type of intermolecular force, hydrogen bonding. That's a big deal. It's so important that it basically gets its own category. Now, ultimately, what happens is you end up with that very positive hydrogen. Do you remember that we talked about hydrogen essentially being naked? Once you remove that electron, all that's left is a proton for hydrogen. It is very, very positive with no electron shielding it whatsoever. So we have that naked positive hydrogen that's super attracted to the lone pairs of electrons on oxygen. And again, this is all familiar from Unit 1. Because of that, we end up with that hydrogen being attracted to the water and actually getting so attracted that it stays on it. Notice the chloride ion, Cl negative, that was there before and it's still there. But this whole entity, I'm circling it in yellow right now and really trying to emphasize it. This is new. This oxygen with 3 hydrogens attached to it and a plus. And looking like this. What? Okay. However, there is no doubt when we continue to do analysis through our past century, early 1900s, that hey, hydrogen as an H plus ion isn't actually there. We have something new. Okay, let's talk a little bit more about it. Dun, da, da, da. This, folks, is known as the hydronium ion. And yes, it's new and it's a big deal. And when it comes to acids, this is the chemical that gives acids their characteristics, like being sour, like being able to conduct electricity, being able to react vigorously with a metal like magnesium. It's hydronium that does this, not just H+. Now, from a molecular perspective, it has 3 hydrogens on it because you added that extra proton on that H+. That accounts for the plus sign here. Right? Think about water. Water has a 0 charge, and when you add a hydrogen ion to that, then we're taking something with a 0 net charge and adding a positive 1. Well, of course you're going to end up with a net charge of positive 1. 0 plus positive 1 is always positive 1. What's our result? H3O plus. You have to still account for every charge in every molecule. Over here, we started with 2 hydrogens, we added 1 hydrogen, so then we end up with 3. We started with 1 oxygen, so of course we still have 1 oxygen, and the charges add up as well. 0 plus positive 1 equals positive 1. Hydronium. Okay. Now, let's look a little bit more about this from a molecular perspective. You have this diagram in your notes, and be aware we are no longer talking about just Arrhenius theory, but we are now in the realm of modified Arrhenius theory. From here on in, guys, I need you, when it comes to acids, that this is the theory you focus on. Acids no longer ionize to simply form H plus ion. Instead, acids now react with water. And that's really key because that's a language that we haven't particularly been using at this point. So water is a reactant with the acid. And when it reacts, and I want you to make sure that you write this into your notes, please, because I'm going to be asking you to do this on all the assignments. This hydrogen is going to transfer, and I want you to actually show it. So that's supposed to be an arrow. And show the H plus that's going to be moving. So we're literally taking this hydrogen and moving it to the water. This is called a proton transfer. Proton because hydrogen is positive and has a single proton. When it moves on to that, our end result is hydronium. And again, hydronium is what makes an acid characteristically acidic. We still have the chloride ion left over, but hydronium is key. Here's that hydronium right here, right? It'll help you to write down the word hydronium, make you write it a few times, get used to it in your brains. Now, we've focused entirely right now on acids, but bases are, of course, impacted by this modified Arrhenius theory too. When you consider, for example, we saw some of the limitations in that lab that you just did. So ultimately, we had a few things that didn't have hydroxide in them and still showed basic properties. They still showed a pH greater than 7. That's weird, right? So the biggest example that was in that one that should have really caught your eye was that NH3. Nothing about that hints to be a base at all. This, by the way, is ammonia. And yet, there's no question it has basic properties. Okay, in a moment, we'll talk a little bit more about why that could be. First, though, that real quick recap of modified Arrhenius theory. You had Arrhenius' theory with a similar blue box on the first page of the notes. Please notice the key distinctions from this modified theory to the original is that acids now react with water, right? Plus H2O. And the other key distinction is we're not forming H plus, we are now forming hydronium. This, guys, is the modified theory. This is the way that we see things happening now. So that needs to be, when it comes to acids, the way that your brain goes at this point. We're no longer forming just H plus. We are reacting with water to form hydronium. Again, I'll talk a little bit more about an Arrhenius base momentarily, but just have an awareness we're still dealing with quite often a dissociation with water. Oh, that's exactly like Arrhenius' theory previously. This, however, is new. Could also react with water to produce hydroxide. Notice we don't have anything new here. Nothing weird like a hydronium. Still just hydroxide. But two ways to get it now. Dissociation or reacts with water. And go back in your brains to ammonia. Okay? And I want you to be thinking about that when we're considering the idea of reacting with water. Okay. So let's play around with these a little bit. We have Arrhenius acids, the old way of thinking of it, and we have modified Arrhenius acids, the new way of thinking about it. And remember what I said, that this modified version needs to be your focus now. But I still want to recap both ways so you're really clear on how to do this. Now, with the old Arrhenius acid, we would have added some water, right? And then it just simply would have ionized into H plus ion plus chloride ion. Done and done. Ionization, we're good to go. With the modified Arrhenius acid, the key difference here is you need to react with water. And that's a big deal. We've never had to react with water before. Next step then is when you react with water, and this is key, guys, I want you to show this in, there is a proton transfer. So I want you to physically show that H plus proton moving from the acid onto water. And of course, when that happens, we end up with hydronium. H3O plus, it is an ion, it is aqueous, right? Don't lose sight of that. And the other thing that we're going to get is what's left over. If you take away this hydrogen, then we're left with chloride ion. Now, chloride ion is negative. Think about the logic of this. If I had an H plus ion and I added it to a Cl negative, I end up with HCl with 0 charge because, of course, a positive plus a negative gives us 0. So the opposite holds true as well. If hydrogen chloride gas had a charge of 0 and I take away a positive 1, 0 minus positive 1, then of course I'm going to get a negative 1 charge. And that negative 1 charge is what is on that chloride gas. Chloride ion. You're going to have to pay close attention to those charges, okay? It's going to come into play, especially on the assignment. All right. Notice the difference though, reaction with water. That's a big deal. Look at this next one, HNO3, which is going to turn into nitric acid, right? Because it's nitrate. So the old Arrhenius theory, we would simply take that and we would ionize it into its H plus ion and into its NO3 negative nitrate ion. Done and done. Da-da-da! Again, is that done though? No, it turns out it was wrong. So instead, we have to recognize that we're going to react that acid with water. Now, how do you know looking at this is probably an acid? That hydrogen is a pretty good hint. And it's the hydrogen that's combined with an anion that's key. If it was just hydrogen with carbon and oxygen, not necessarily. But with an anion, oh yeah, we've got an acid. Okay, I combine those two. Next step that you need to show is the proton transfer. That hydrogen, proton, H plus, is going to move to the water, which means we are going to end up with the lovely hydronium. And with hydronium, if the hydrogen has left, you have this anion still there. Think about the charges again. Originally, this is a charge of 0. So if I take that 0 and I subtract a positive 1, I end up with a negative 1 charge. And that is the charge on nitrate. You could look on the polyatomic table of ions on your periodic table and see that too. It is NO3 negative. So use those as little cheat sheets, right? That helps you. But make sure you're getting the charges done correctly. Okay. Check it out then. Arrhenius acid versus a modified Arrhenius theory. This is now the way things should be done. Let's move on. Arrhenius bases, guys. Now, all that I've said so far is, hey, these can form by either dissociation, number 1, or number 2, by a reaction with water. Now, here's the key thing, and take note of this. It will always be dissociation if you see hydroxide in the formula. So that means that an Arrhenius base and a modified Arrhenius base, as long as you see hydroxide, it's the same. I'll show you what I mean. When I put this barium hydroxide in water, it dissociates. I end up with barium, take the correct charge, it's 2 plus, according to the periodic table, plus, and don't forget about this, guys, there are 2 hydroxides, therefore I need to put 2 hydroxides as a product, aqueous. Dissociation, done and done. Hydroxide is present, so the modified Arrhenius theory is identical. Ba2 plus, aqueous, plus hydroxide, aqueous, done. No difference whatsoever. Take note. Okay, check out the next one, potassium hydroxide. Once again, you see that hydroxide. You see that hydroxide. This is an ionic compound. We have a metal with hydroxide, cation, anion. So that means, again, same. This is simply going to dissociate. We're going to end up with our K plus ion plus hydroxide, only one of them in this case. And with the modified theory, it's identical. Dissociates to the K plus ion plus hydroxide. Done and done. Okay, no difference between the Arrhenius base and the modified Arrhenius base. If, again, I mentioned this before, if you're dealing with simple dissociation, then they're the same. But here comes that weirdo from the lab again, that NH3. Now, when we did this in the lab, of course, it was in solution, so it was NH3 aqueous. Ammonia naturally is a gas, and it's kind of a nasty one. It's quite dangerous. You certainly don't want to be breathing it in. Now, if you look at that formula, there's absolutely no hint of hydroxide there, and yet it acts as a base. So that means somehow, some way, we have to get hydroxide. The way we do this is not dissociation, but remember type 2 reacts with water. That's key. Now, if you think back to what water is, guys, I can rewrite water as HOH. It means the exact same thing. And when we're focused on a base's reaction with water, there is still a proton transfer, but it's going the other way. Instead, you're transferring from the water to the base. So it's not going, as it did with an acid, from the acid to the water, but instead it leaves the water and goes to the base. And you can see that more easily here, right? Here's the proton that transfers, the H. And then consider what's left over, OH. All of a sudden, things should be starting to go ding, 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 and clicking in your brain, okay? Like I said, I think it really helps sometimes to write water as HOH instead. When we do that, think about this. You added a proton to NH3. So now we have NH, not 3 of them, but 4. And you added a proton with a positive 1. That positive still has to go on there, okay? NH3 had a net charge of 0. So when you take 0 and add 1, you get positive 1. It's aqueous, of course. Now the hydrogen came off. What's left over? I'm going to highlight it kind of a turquoise here. OH. There we go. And that's what we have left. Plus hydroxide, which is key. This hydroxide is what gives us our characteristics of a base. How does it come with some weirdo like ammonia? Well, because the ammonia reacts with the water, thus allowing for a proton transfer and water to lose that proton, and you're left with hydroxide. Let's talk about this a little bit more, okay? This is important, guys. I'm obviously focused on it quite a bit, so make sure that you have this case of NH3, which, make note of it, please, is ammonia. This is one to memorize, okay? This case of ammonia still has a lot of the properties of a base, and I'm not going to write them all out, but it's bitter, it turns litmus paper blue, it shows a pH greater than 8. When you put it on your hands, it feels slippery. It is definitely basic. It's still, here's a weird one, it still conducts electricity. You don't see any ions there, and yet somehow ions are present. Now, this formula you can rewrite if you want. It's the same one we just did. But make sure if you haven't already that you're really, really key on that proton, H+, transferring this time from water to the base. And we end up with that characteristic hydroxide. Okay. This visual is also in your notes. And I just want to make sure that you're really, really clear on what's happening. One of our hydrogens moves. It is now over here when we have it as ammonia, which is going to be a positive charge. And here's our hydroxide left over, negative. The charges are important, guys, right? Ammonia is a cation. Ammonium, is a cation. And here's your negative hydroxide. I'd recommend that you write down what each of these different entities is so that you have their names. This first one here, ammonia. Second one here, of course, is water. Now take note, and this is on your table of polyatomic ions. This is no longer ammonia. This is now ammonium ion, right? Ammonium. And this, of course, is hydroxide. There they are. Okay. We'll do one more example to make sure that you can see there's other circumstances where this occurs. Take note of it, please. You're going to have to do this in your assignment this week. Oh, and where did I put it? I see I don't have it here. Okay, I'm going to put this example on this page here so that you can still see it. The example we're going to do is at the bottom of the notes, and it's HCO3 negative. This is actually similar, guys, to what you had in the lab, but there we had it as sodium bicarbonate, right? This dealio. And sodium bicarbonate, what happens here is it first dissociates, and then you're left with a bicarbonate ion, which is what we have here. Notice there's no hydroxide here, and yet it absolutely acted as a base. How do we know? Well, because we ended up with litmus paper turning blue and ended up with a pH greater than 7 in the lab. No hydroxide there though, right? The H and the O aren't together. So what do? We react it with water. Take note, you're going to need to do this in your assignment. In the assignment, it'll be pretty clear. The question actually says to you, hey, each of these is going to react as a base with water, right? So it'll tell you this is going to be a base. When it reacts with water, key thing is that proton transfer, where hydrogen is going to move from water to the base. In terms of how that happens, look at the numbers. Previously, there was one hydrogen, but we're adding another. So now you're going to have H2. Okay, started with one, added another, now we're at H2. The CO3 is still there. Notice the charge though. Now it's at 0 because originally there's a -1 charge. We added the +1 proton. That gives us 0. Okay, what's left over? Well, if the hydrogen left from the water, remember what I said, it's easier to think of it as HOH, right? And then this hydrogen leaves. We end up with a hydroxide. Never forget hydroxide is negative. It's an anion. And again, it makes sense. The positive hydrogen leaves. We started at 0 for water minus a positive hydrogen. Of course, you're going to get a -1. All right, folks, there it is. That's that last example that is in the notes. And be aware, generally speaking, when you see an anion like this, an anion has a negative charge, it will often act as a base. Try out the questions that are in your assignment, number 2 and number 3. Go back, listen to the podcast if you need to, and good luck to you. As always, let me know if you got questions or concerns. See you later.